Okay, well, I would like to thank the organizers for having me, and especially Arnab for making this online version of my talk possible. So I will mainly be telling you today about some very recent results we obtained in collaboration with a group of Ben Leff at Stanford, and they are already posted or published in these two publications. So there are two topics of this talk that are recently have attracted quite some attention. One is the topic of many body scars. I saw there are several talks touching that topic in the conference. And what is going to be probably different from those other talks is that these many body scars I'm going to be talking about, I'm going to be showing you dynamics very far from equilibrium. Now, the other topic is that of near-integral one-dimensional quantum systems. And early in the introduction, I'm going to be spending quite some time trying to make clear what I mean by near-integral. So, okay, so let's get started with the introduction. What is it that I mean by near-integrable? So these are systems that are creating in optical lattices, and one essentially generates an array of quasi one-dimensional gases, and they are very cold. The interactions for most standard gases that you load in this optical lattices at this very low temperature is of the contact type, and you see it in here. And this contact strength is something that can be controlled experimentally by changing the transfer confinement and changing the scattering length. And actually, Ben Leff group is going to be using fetchback resonance to change this AS and change this G1D. Now, when you have, in the homogeneous case, when you have bosons interacting with contact interactions, and in translational invariant system, this is nothing but something that we describe with the Lieb-Liniger model, which is integrable. And when this G1D is infinity or very large, then one has the Thom-Girardot gas that maps into non-interacting fermions. Now, how is it that we see integrability in those gases? So the first thing is that if you prepare them in equilibrium, their equilibrium properties can be described by this Lieb-Liniger model within the local density approximation because there is a trap. And there are a few papers that have studied this. And in particular, in this one, they studied this G2. And what you can see here is the points are the experimental data, and the line is the theoretical calculation within the local density approximation in the Lieb-Liniger model. So that's the first thing. You look at in equilibrium, you can describe it using the Lieb-Liniger model. Now, when you take it out of equilibrium and you wait for it to equilibrate, because these systems are integrable, what happens is that the momentum distribution function and other quantities, they don't equilibrate to the thermal prediction. So these are resolved for different gammas in that experiment. And this is how gamma is defined. You see, it's a function of G1D and of the density, and Dave Weiss actually changed the density to change gamma. And for all the gammas that he could study that the system was one-dimensional, the momentum distribution function didn't look thermal. So this is what you would expect for the thermal momentum distribution functions, is this dashed line, and you see this is far from it. And we now know that to describe what happens at long times, one needs to use a generalized Gibson sum. Now, this is incredibly robust, even though you hear that integrable systems are fine-tuned and so on. So really, in those experiments with only contact interactions, that's all they saw. I mean, after that, they had losses and they lost the experiment. So they never saw thermalization in those systems. To see thermalization, one needs to introduce integrability break in terms that are stronger than the trap. And this is something that Ben Leff can do in his group because he can introduce dipolar interaction. Now, this what is shown here is the evolution of the momentum distribution function after a Newton's cradle pulse. And this is what happens in 3D. Okay, and this is in terms of the periods of oscillation in the trap. And here, if you want to see it in milliseconds, and you see that after 7 oscillation period in 3D, the system, it essentially equilibrates to the thermal distribution. So if you go to 1D, is what you saw before in Dave Weiss experiment, you don't see the thermal equilibrium. But then Ben, what he can do is, let's say at this given time, he can change the angle of a magnetic field to tune the dipolar interaction. And he can then, for very long times, you see up to 3 seconds, he can study the evolution of the momentum distribution function for different angles. And what you can see is that evolution towards the thermal distribution, in which the time now depends on the angle because it depends on the dipolar interactions. So one can actually quantify. So if you look in here, you can quantify what is the distance to that thermal distribution and plot it now as a function of time. And for different angles, you see always the same behavior. So some fast dynamics that you would expect, say, in the integrable model, and then some very slow approach to thermal equilibrium. And one can fit this to exponential and get a rate, and that rate was consistent with being proportional to the integrability breaking strength squared. And we've also looked at this numerically using an LCEs and in the XXE model, and one sees the same. So one have the XXE model, introduce next nearest neighbor interactions as integrability breaking, then one sees fast dynamics, and then this low equilibration whose rate is now proportional to the square of that integrability breaking perturbation strength. So, and as a matter of fact, this is not unique to integrable models. So any model, even if you have a quantum chaotic model and you have a conserved quantity and you weakly break it, what's going to happen is there's going to be a slow dynamics, and one can describe it using a Fermi golden rule modified for the specific quantity. And I can show you here results of numerical experiments in which we use an LCE to compute the rate and this formula for a non-integrable model in which we broke particle number conservation, and you see that it perfectly matches the theory. If you want the numerical evaluation of this expression, matches the NLC result. So what do we mean then in this context by near-integrable? Is these are systems that at short time, the dynamics is that of the integrable model. And then they will have a long thermalization time, and that's not what is going to be probed in the rest of this talk. Okay, so all this talk is going to be to what happens in this very short time that the dynamics is stated by that integrable model. Good. I can take questions. So if there is any quick question, I can take it. But if not, let me then move on. So in recent years, the new exciting thing that we've done in the context of these near integrable systems is that now we can measure the distribution of the conserved quantities, if you want, the rapidity distribution. So let me tell you how this is done. So this is actually a development after I was there in the ICTS in 2019. So how is that measured? So let's see what happens. And this is something I was interested in when I was a graduate student. So because at that time, people were doing time of flight experiments. And then my question was, what happens if you do time of flight, but in the presence of interaction? So essentially what happens, for example, if you have a model of hardcore bosons, okay, you have them in the trap, and you let them expand in one dimension in the presence of interactions. So now let me show you the evolution of the density and the evolution of the momentum distribution function. Now those bosons are mappable to fermions. So this is the bosonic distribution, and this is the fermionic one. Now the fermions, remember, they are non-interacting. So if you would have fermions and let them expand, that wouldn't change. And this is what you see for the bosons. So the density is not very exciting. What happens? Well, the system expands. But you see that the momentum distribution function matches the one of the fermions. So if you let the bosons expand and you measure the momentum distribution function, what you will see is the momentum distribution function of the fermion, which is nothing but the rapidity distribution, the momentum distribution of the conserved quasi-particles in the model. Okay, so that's exciting. This is something that was done recently in the group of Dave Weiss at Penn State. So he essentially had those gases in the trap, let them expand, and at different times in the lattice, he shut off the lattice, did a time of flight experiment, and then measured the momentum distribution function. So this is what he observed, and you see this transition for a bosonic shape to a fermionic shape. Now, if we do the theoretical calculation, this is what we see, and we see exactly the same as he does at long times, but at short times it's not quite so. And this is because they have finite time of flight effect. So they can only expand for so long and take the picture. So for this case of the TG gas, we know all correlation functions exactly. So we could actually do the evolution up to the time they did it in the experiment and then in 3D. And this is what you get if you do the evolution in 3D. So now you see it's almost identical to the experiment without free parameters. This is a one-to-one comparison between theory and experiment at different times. And only at T0 is that we see some differences, and this is because the theory is done at 0 temperature. So this is now at the longest time, and here you see there are 4 curves. So there is one from each of these plots at the longest time, and then the fermionic distribution is in green, and you see that they all match. So this is kind of showing that in the experiment, one can measure those rapidity distribution. Okay, so and you will see in the rest of the talk, on the talk that usually the rapidity distribution is slightly narrower than what the experiment sees, simply because it's done for some finite times, and to get the exact rapidity, you would have to do infinite time. But the difference are really very small. So good. So now what we can transition and see, well, what happens now if you have dipolar interactions, okay? So I'm going to tell you very quickly, I'm going to go through how we model, how we think of this system. So the first thing is that we forget about the dipolar interactions between different tubes in the experiment. So the setup is like the one in the Wise, except that now we have these dipolar interactions. So we think of them as independent 1D models. So you see they are moving, there is a trap, there are contact interaction, and the dipolar interactions. So the dipolar interaction within this single mode approximation, they have this form. So you see it has a contact part and a regular part. And what we do is that this breaks integrability. And what we do to deal with that is we just put that all in the contact part by computing the integral. So all the calculations that I'm going to be showing you later are done on precisely the linear model that I showed you before. And the only difference is that this G1D is not only due to that van der Waals part, but I put all the DDI dipolar interaction contribution into the contact. Okay, so that's why I will be able to do calculations using integrability and account for effects of the DDI because I am plugging it in the contact part. Okay, so then now for those experiments, we didn't quite have the spatial resolution that we had before with Dave Wise, so we didn't know what the distribution of atoms. So let me quickly tell you how we model them. So we think of this theoretically as having, this 3D BEC that as the 2D optical lattices ramp up, at some point the system decouples, okay, into individual tubes, and that doesn't need to happen at the same lattice depth for all tubes, but we assume that it does. So this is the first thing we do in our modeling. So we think that there is a lattice depth at which all tubes decouple into individual tubes. So there will be some number of atoms in each tube, and we assume that they are all in thermal equilibrium, okay? So these are 2 parameters of our simulation, the depth at which they decouple and the temperature, okay? So we determine the number of atoms and the entropy at that point, given this T and U. And then what happens after they decouple? Well, the system continues evolving, but now we are not assuming that the 1D tubes are in thermal equilibrium, but we are assuming that each of them is carrying an adiabatic process. Okay, so the entropy doesn't change up to the end of the process. And then with the final parameters, we can compute the temperature of each tube. Okay, so now our fitting parameters then are this lattice depth at which they decouple and that temperature. Now let me show you the comparison between the theory and the experiment with those fitting parameters. So this is in the TG regime in which they use a fetchback and they are very close to infinity. So now what we have here is we are taking this lattice depth to be 5, and we can change the temperature and see what is the difference between theory and experiment. So this plot, this is the rapidity from the theory, the experiment, the momentum, the theory, and the experiment is taken at the optimal temperature here. So, and you see it's quite similar in the TG regime to what we saw in the F1 experiment. The rapidity is slightly worse, the agreement. Now, when we decrease gamma, and of course, if we decrease gamma, the density of the gas is going to increase and dipolar interactions are going to increase. what we see is that the agreement between theory and experiment degrades. So you see the momentum distribution function slightly different at the tails, and the rapidities are more different. So let me just tell you a few things about this matching between theory and experiment. So the first is that the theoretical results do not depend strongly on the lattice depth. So it looks like it's a reasonable approximation to think that they decouple or at the same depth. Now, one interesting thing that we found when we were doing these calculations is that Ben had estimated the BEC temperatures. And when we estimated the temperatures at the decoupling time, they were lower. So it's like the system cools when going between 3 and 1D. And there is a full paper by Christoph Nagel recently just discussing this in great detail. So, and the final thing is that the agreement between experiment and theory, it worsens as one decreases gamma. So as one goes towards the weaker interaction regime, because the DDI starts playing a more important role in the equilibrium properties. So we've estimated the intertube DDI, and it seems to be of the order of 4% in the TG regime and higher 5.56 for lower gamma. So in this regime is around 5.5, and in this one is like 4. Okay, so this is now, and this is the important thing, is in the experiment, these the decoupling time and the decoupling depth and the temperature, they are fitted for describing the experiment only once. Because what Benz does is he prepares the gas, he loads it, he goes to one point, and then adiabatically he will access many other regimes, different gammas, and he will also change the dipolar interaction. So this is what he does. He goes into this 55 degrees at this gamma, and then he changes. Now you see these are the different colors, the angle. And that's what it's telling you is in this regime, in this plot, what we are seeing is what is the effect of changing the dipolar interaction. The contact is not changed. So, and then he can, at this 55 degree, go to other gammas by changing the contact interaction using the Feshbach resonance, and then again changing the angle to see the effect of the dipolar interaction. Okay, so let's see. So you see, if you are in this regime, you see that the dipolar interaction does affect, okay, the momentum distribution function and the rapidity. If you go to even weaker interaction, it affects it even more. And if you go to the TG, it almost doesn't affect it. Now, if we do the theoretical calculation, we should put the DDI in the contact. This is what we get, matched experimental results. And this is telling us, this is ongoing work, that we need to do better to account for the effect of the DDI in here. Now, the rest of the talk is going to be in this regime. Actually, for gammas that are much larger than this, is in the TG regime, which is where we can go and play with the scars. Okay. So then now, remember, now we are going to the limit in which gamma is going to be large. And how is it that these scars are created? This is from a previous work of Ben and Saran. So what they notice is, you see the previous, all the results I showed you were when the interaction were repulsive. What they notice is they could go with the Feshbach resonance and go to attractive interactions. And they found that the states in the attractive interaction were stable. Okay, so you can see what one can do. Feshbach resonance, one can change this gamma. Everything I told you before was here. But you can keep going and get to negative interactions, and they could see that the gas goes stable. And how did that happen? That happened because apparently the repulsive short range part of the DDI was helping with the stability. Now, these are the scar states I'm going to be talking about. Okay, so why are they scar states? So in the ideal case of you preparing initially a 0 temperature state on this part, when you go in this regime, that state has a logarithmic entanglement entropy with the size of the system, is very non-thermal. And the other important thing is that you see it has no like cluster states, right? So you put attractive interactions, you want to create lumps of particles, they are not there in this branch. Okay, so that's what I mean by scarce states. And since I'm going to be showing you result for all these regimes, to remind you which point I'm dealing with, I'm going to have a sketch of the two particle wave function, just telling you this is repulsive, this is the TG, this is what I call the scarce state. This I will call it a supertongs, and this is a weakly attractive gas. So good. So this is now in these supertongs. Now you see this is negative gamma. The comparison between the theory in dashed lines and the experimental result for the rapidity and the momentum distribution function. This is what we use now to fit our decoupling depth and the temperature. And the theory is done here just in the infinite repulsive limit. Here's the temperature. So you see very sharp low minimum at 15 nanokelvin and almost independent of the lattice depth. So that's what we take. We take this point, and now we compare with all the other cases. Okay, so this is repulsive, this is the scarce state, this is a weakly interacting. And here in this regime, we cannot obtain result for the momentum distribution. So all I am showing you here is comparison between theory and experiment for the rapidities. And then, well, these are the experimental momentum distribution. So you see in the weakly interacting regime, rapidities and momentum distributions are similar. Okay, so now we have this in equilibrium, and what we're going to do is take it far from equilibrium. And to do that, to study that theoretically, we are going to first study the TG limit that we can fully simulate, and then use GHD away from it. So now this is the dynamics after 10 times trap quench. So the trap is changed by 10 times. This is the dynamics of the momentum, of the rapidity, and then you see the theory are the dashed lines and the experiments continuous lines. So we see here a small difference, but we see that the experiment and the theory agrees, and that's amazing. That tells you how stable that highly excited state is in the experiments. And this is now how the full width Hall maximum of this distribution evolve as a function of time for the rapidity and the momentum. And you see that experiment and theory are very close to each other. And actually, this dip is something that was called a Bose-Fermi oscillation in the TG regime, and it was also something that was observed by Dave Wife in his experiment. So now the exciting thing is to move beyond the TG and look at what happens in the scarce state. Okay, so to do that dynamics, we are going to use this recently developed GHD theory that uses the idea that locally the system is always equilibrated to a GG, otherwise it's similar to what you do hydrodynamics. And this is the GHD equation, which looks like a continuity equation in the presence of a potential, but in this equation, all the interaction, all these nonlinear effects are in this V effective, that is the solution of in this integrable equation, and the scattering length is the interactions that determine this scattering amplitude, and this is included here. So once you solve this equation, you get these rows, which now you see depend both on the rapidities and the positions. And then you integrate it with different functions in here, and you can get particle density, energies, and so on. So that's how we obtain those results that I'm going to be showing you there. Okay, so this is now the experiment versus the theory for the evolution of those rapidity distributions using GHG. For the repulsive, this scarce state, remember, that's negative, but gamma is not minus infinity, it's of the order of minus 20, and this is the weakly attractive. And you see it's all very similar to what we obtain for the TG limit. So the experiment also in this scarce state is stable enough that within this first oscillation period, what we get is very similar in the theory and the experiment. And now we can go and look into the details of what's happening there. Okay, so if you look at now what I'm showing you here is if you integrate those rapidity distributions with weighted with the p square, or the rapidity square, what you get is the total energy. Now, what does it mean total energy here is really the sum of the interaction plus kinetic energy, right? Of course, the total energy is conserved because there is also a trap. So this is just the sum of the kinetic and interaction. And the reason it can go up is because the trap energy decreases. So when the gas is compressing, the trap energy decreases, that kinetic flow interaction goes up. And you see that the theory and the experiment are almost on top of each other for that total energy. Now comes the surprising result. So if you look at the now kinetic energy, okay, so now you look at only the kinetic part, you remove the interaction part. So you see that here is qualitatively the same, the theory and the experiment misses a little bit, and here also. Okay, so in the middle, what happens at the maximal compression is that the kinetic energy decreases. So in the repulsive case, we can understand that, because as the gas compresses, kinetic energy starts going up, but at some point part of it becomes interaction energy. So we understand why there is a dip here. For the weakly interacting case, interactions are irrelevant, so the kinetic energy goes up. So this is where the surprising finding is. So in the attractive case, in which this is the theory, what you expect is as the gas compresses, because the interaction energy is negative, then the kinetic energy should go up. And if you look at the experimental curve, it really looks like if the gas was repulsive. So that was surprising. And actually, one can look at the momentum distribution functions, which are used to compute these kinetic energies. And for the part that was used to compute these kinetic energies, right, one has to integrate that with the k-square. So the attractive and repulsive cases, they look qualitatively the same. But there was an important difference that was not taken into account in this calculation, which is that a tail developed in this state. Okay, so, and that tail is surprising if you can see it in here, because, for example, after like a lot of statistics, so 2% of the atoms are in there. And if you add this to the kinetic energy, you end up having 20% of the kinetic energy in that case, compared to the repulsive case that there is nothing there. So now, how different is what is happening here? This is at maximal compression with before and after. This is something that you can see in here. So this is the repulsive case. And now the lightest color is shortly before, and the darkest is shortly after. So if you look at the repulsive state, not much is happening in the tails before, after, or at maximal compression. Right now, if you look at the scar state, you see it in here, then you see that these tails really develop at the maximal compression point. So this was the cutoff that was used in the original and what I showed you before, calculation of the kinetic energy. Now, after doing a lot of statistics there, Ben and his group were able to add more of the contribution of the tails. It really doesn't change anything for the repulsive case. But you see now, if you do it in the attractive one, it fills up this dip. And now this is what happens when you include all these bosons in here. But still very far from the actual expectation for the kinetic energy, which would be this. This would be the total energy interaction plus kinetic. So essentially, for these scar states at maximal compression, what seems to be happening is that there are very high momentum particles, likely very few of them, and they are carrying that all that excess kinetic energy. So one cannot see. So for all the bosons that one can essentially see, and for example in this regime, it behaves like if they were repulsive. You add this part, you get a bit more, but there are bosons there that we cannot account for. So and now the challenge is whether one can see those, one can measure them, or that's impossible experimentally. So with that, I'm going to conclude so that we can have a lot of discussions. So what is it that I have been showing you here? So first is that these dipolar quantum gases are interesting, going beyond the pure contact interaction, because they allow you to study the effect of the integrability breaking, and you can look at prethermalization and compute rates and so on, and compare with the theory. So they are also a unique setup for precision many-body physics. So as you saw, there are effects from the long-range dipolar interactions, which somehow the leading part we were able to capture, but there is still a lot to figure out if one wants to have a quantitative agreement between the theory and the experiment. So we are working now on that. And the other thing is that one can generate these novel scarce states. And remember, what I mean by scarce state is one crosses to the attractive side, and you end up in a very highly excited state with low entanglement. And what is amazing about those states in Ben's setup is that not only you can create them and study their linear response, which they did in the previous paper, but you can actually change strongly the trap, and you can study the far from equilibrium dynamics. I show you that this is something that one can describe theoretically using GHD, but there are unaccounted for bosons, if you want, at maximal compression that now one needs to see if one can find. And the important thing is that you see, as the system then expands again, you could see in the plots that we could account for all the interactions. So it's not like something goes missing and is gone. So when we study the dynamics at later times, we can see the matching between the theory and experiment. So there was no violation of energy conservation or losses at that maximal compression point. So with that, I'm going to stop. I'm going to thank my collaborator. Ichen was the one that did all the theoretical calculations here. I show you some results from Dave and Ben's group, and then, well, thank you for your attention.
Hi, Marcos. Yeah, this is Arnab. Yeah.
Hi, Arnab.
So Liebniger model, they host some kind of bound state, many body bound states, right?
Yes.
So, so if you put a dipole-dipole interaction, can you treat it perturbatively, and that probably can explain why the scars are stable? Is that anything to do with that?
I think there is a paper that tried to explain the stability of the Liebniger model, but I cannot comment very deeply on it. But yeah, work has been done on explaining that. So at this level is just what Ben and Sarang had done before was just phenomenological, right? So they created the system, and when they put the DDI to be repulsive, it was stable. But of course, they could control like removing the DDI in the tubes or making it attractive, and then the gas was gone. So they know for a fact that they need this DDI to be repulsive, and indeed there is some theoretical work now trying to understand why.
Okay, thanks.
Any other questions? Okay, well, if not, let us thank Marcos one more time.
Okay, well, thank you.